Welcome to This Explainer. Today, we're going to unravel a high-stakes whodunit mystery that has literally been haunting Oracle developers for decades. You know, in the world of Oracle SQL, there's an actual ghost in the machine. It's this phantom bug that lives completely invisibly in the gap between your filters and your sorting. So we're going to shine a massive spotlight on this logic gap, we're going to master deterministic Oracle queries, and finally, we're going to hunt this ghost down for good.
Okay, let's dive right into this. Have you ever had a bug that only appeared when you added an index? Honestly, it sounds completely impossible, right? Indexes are supposed to speed things up. They aren't supposed to magically change your actual data. But imagine this scenario for a second. You're a database administrator at a high-frequency trading firm. The boss urgently needs the top 5 largest trades of the day. So you run a quick query, the data looks perfect, and you hand over the report. Awesome. But a week later, you decide to optimize that exact same table by adding a new index on the trade date. And suddenly, your top 5 report completely changes. It's returning totally different trades and different amounts. You haven't touched a single line of code, but your data completely shifted. Why? Well, this phenomenon is exactly what we call the phantom bug. This issue stems entirely from relying on non-deterministic SQL. Relying on this kind of unstable query architecture is essentially sitting on a ticking time bomb. I mean it. It might work flawlessly on your machine today, but the very moment the physical database environment shifts even slightly, like, say, an index being added, your results become entirely unpredictable. Your critical, highly sensitive top 5 report, it's suddenly just a random 5. All right, moving into our first section, the execution order trap.
To understand exactly how this phantom bug operates in the shadows, we have to interrogate our prime suspect, the processing logic of the Oracle SQL engine itself. The absolutely crucial point here is understanding the vast gap between human logic and database logic. The logical trap that developers fall into is assuming Oracle operates the way our brains do, right? We assume that it sorts the entire table first and then simply picks off the top n rows. But if we look at the actual flow, it's a completely different story. In a single query block using rownum, Oracle picks the first n rows it encounters, and then it sorts only those specific rows. You aren't actually finding the top 5 largest trades in your entire system. You're blindly grabbing 5 random trades and then sorting just those 5 amongst themselves.
Let's move on and see how this builds directly into the database's internal lifecycle. Step 1. The from and join clauses identify the data sources. Step 2. This is where the where clause applies its filters and, crucially, this is the big takeaway, this is exactly where the rownum pseudo-column is assigned. Rows get numbered the exact second they arrive from the source. Step 3. The order by clause happens. Notice anything weird? The sorting occurs completely after the subset is already locked in by the rownum filter. The sorting happens far too late in the process to actually be useful.
To really intuitively ground this concept, think of it like taking a ticket from a dispenser at a super busy deli. You get your number as you walk in the door. It doesn't matter if you're the most important customer in the whole city, or in our database case, the row with the absolute highest trade value. Your number simply depends on when you arrived at the entrance. Because rownum is assigned right at the door, it makes it fundamentally impossible to guarantee you're getting the tallest or best records before the sorting actually happens.
Section 2. The accidental success illusion. So now we need to talk about the highly dangerous false sense of security that actively tricks developers when their broken code appears to work perfectly in development environments. We call this the index trap. Why on earth does fundamentally flawed code survive testing? Well, it comes down to physical dependency. If your data happens to be naturally inserted in perfect order, or if the optimizer just happens to use an index full scan that coincidentally matches your desired sort column, your broken query will successfully return the correct results. But it's succeeding by pure dumb accident. The rows are just fetched in order by sheer luck. The exact second that index gets dropped, or your data volume grows and the optimizer decides to switch to a full table scan, your production data breaks instantly.
Section 3. Proof in the engine. I know that database engineers are naturally skeptical, which is a good thing. So let's look at the hard forensic evidence directly inside the engine. Let's clearly map out the exact syntactical difference between failure and success. Take a look at the traditional broken query. You filter by rownum less than or equal to 10, and then try to order it. This is highly volatile. It slices the data first and then sorts it. But look at the classic correct method, using an inline view.
Notice those parentheses. You are forcing the database to sort the entire table inside that subquery first, and only after that sort is 100% complete do you apply the row num filter on the outside. This is completely deterministic. It correctly sorts first and then slices. And this brilliantly illustrates what's really happening under the hood when we pull up the execution plans. In the broken query, you're going to see a specific operation called count stop key. This literally tells us Oracle blindly stopped reading the table as soon as it hit your count limit, completely ignoring your broader sort requirements. But in the correct query, look really closely. You see sort order by stop key. The database is actively maintaining a special high-performance memory sort buffer. It retains only the actual best rows as it scans, rather than just stopping arbitrarily. It all boils down to this quote: that one word, sort, makes all the difference. Spotting that single word in your execution plan is your ultimate forensic proof. It literally guarantees whether your application's results are going to be completely random or 100% accurate and totally deterministic.
Section 4. Sort, then slice solutions.
All right, now that the mystery of the ghost in the machine is thoroughly solved and we actually understand the mechanics, it's time for the ultimate relief, the deterministic solutions you can implement today. Let's visually reinforce the journey we've taken using this flow showing the trap, the failure, and finally the fix. Notice how the inline view totally resolved the evaluation order issue. By forcing the order by to execute inside that inner subquery, you're establishing a persistent sort queue. The database accurately evaluates the dataset, it sorts it correctly, and only then does the stop key gate drop to hand you your precise, predictable output. Now, what's really interesting about this slide is that there's actually an even better, more modern approach if you're on Oracle 12c or newer. Take a look at this modern ANSI standard syntax, order by amount DESC, fetch first 5 rows only. It's just incredibly clean. It's elegant to read. And most importantly, it directly and explicitly tells the optimizer your true intent without requiring you to build nested inline views or play weird games with pseudo-columns. Finally, Section 5, audit, modernize, and verify. Let's shift gears to the practical application of everything we've just covered, highlighting exactly why you and your team need to care about implementing these solutions immediately. Fixing this trap achieves 100% risk mitigation. Think about the massive business value here, guys. Inconsistent reports lead to management mistrust and super chaotic troubleshooting sessions. By utilizing a correct top-end implementation, you directly restore that trust. You ensure an identical, absolutely unshakable truth, regardless of whether your data volume swells from 1,000 to 1,000,000 rows, or whether some other admin changes your indexes in the background. The return on investment for standardizing this across your codebase is immense. It completely eliminates those volatile Heisenbugs where reports vary wildly between your dev and prod environments. It absolutely guarantees deterministic top-end results every single time. It prevents massive, system-crashing full-table memory sorts while dynamically triggering that highly efficient stop-key optimization buffer we explored earlier. Oh, and as a quick pro tip, remember to utilize the with ties clause if your business logic requires you to handle matching values at the very end of your list.
Here is the grand finale mantra you need to remember. Sort, then slice. This is the definitive rule you must take back to your desk to maintain absolute consistency and actually trust the data your databases are outputting. Sort your data, then slice your data. Never, ever the other way around.
So, I'm going to leave you with this provocative challenge. Are you ready to audit your codebase and clear the ghosts from your machine today? I strongly urge you to open up your code repositories. Do a global search for any instance where row num less than or equal to is paired with an order by in the exact same query block and refactor them immediately. Stop this phantom bug before it ever has the chance to hit your production data. Thank you so much for joining me for this explainer. Now get out there and write some bulletproof SQL.